So welcome to our second seminar, and today we're going to talk about how understanding the nature of light led to the development of quantum mechanics. So this is part of a trilogy, if you will. Understanding the development of light led to the development also of special relativity and our modern theory of cosmology. So it's really amazing how the intricate nature of light has led us to a understanding of the universe that's much different than it was, let's say, 100 years ago. So light is the primary sense that human beings have. Almost all of the information we gather as individuals comes from observing with light, with our eyes, the things around us. And this is a very picturesque scene of Monument Valley, you may recognize. And in the background is the Orion Nebula up here. This is Orion is the hunter, and one of his shoulders is the bright red giant star Betelgeuse, and one of his feet is the bright blue giant star Rigel. And this creature over here is the planet Mars. This is a very long exposure, and so the planet Mars being close looks quite overexposed, but it's a beautiful picture. And as far as we know, this is the only place in the universe where you can breathe the atmosphere and look through the atmosphere and see the universe unfold before you. And we should never forget how beautiful our universe is. Okay, so as I mentioned in the introduction, light is a unique phenomenon of nature. There's nothing else in nature that's quite the same as light. And understanding all of its nuances has led us from classical physics, ending, let's say, in the year 1900, to the development of all of the modern theories of physics, quantum mechanics, relativity, and our modern understanding of cosmology. So let's talk about what are some of these properties of light that led to the development of the quantum theory. And the first thing we're going to discuss is the distinction between particles and waves as they were viewed in classical physics. Much of what we're going to talk about are things that many of you have heard before from me, and others have not. So for the first group, this is going to be a brief review, and for the others, you'll have to run fast, I guess, to get up to speed, because a lot of these ideas are really very profound. They're not complex to say, but it takes a long time before you can really wrap your head around some of these notions. So let's talk about classical particles and classical waves. Now, classical particles were viewed to be very simple objects, very miniature versions of ball bearings or something like that, simple ball-shaped objects. But waves were clearly more complicated. So as I speak, I'm putting pressure on the air molecules in front of my mouth, and those push on the air molecules beyond them and beyond them and beyond them and so forth. And so a wave of pressure propagates through the air as I speak. And graphically, we will push on this first level layer of atoms on the left, and they push on the next one, and they push on the next one, and so forth. And so this wave of action propagates through the assembly of air molecules. So the first important thing to realize from all of this is that a wave is not a thing in and of itself. A wave is the organized motion of other things. In particular, a sound wave is the organized motion of air molecules. So a wave needs these smaller entities, which are called a medium, to propagate through. And the velocity at which the wave moves has got nothing to do with the source. and it's entirely determined by the properties of the air molecules that are doing the moving. So the sound of my voice, the sound of a car, the sound of an airplane, and all other sources of sound all propagate through air at the same speed as we described, the speed of sound. We don't have to say the speed of car sound or the speed of human speech. It's the speed of sound, which is determined only by the properties of the air molecules that the wave is passing through. And this is all very different from particles. Particles don't need a medium. Particles can travel at any velocity in classical physics, and the particles are themselves a thing and not just motion. So in the year 1900, classical physicists, classical physicists viewed particles and waves as two completely distinct entities. Everything in existence was either a particle or a wave with no overlap between them. And the particles had all these properties on the left, the waves had all these properties on the right, and there was this great wall that separated the two entities. And light was known to engage in diffraction and interference, and it followed a wave equation, which we'll show later. And so it was clearly on the wave side of the Great Wall. Particles didn't need a medium, as we've discussed. Particles came in integer quantities. You had 1 or 2 or 3 baseballs, but never 2.5. You could have a wave of any height you wished. Particles were clearly localized in small areas, and waves spread out to fill all the available space. So they really were extremely different entities. And as we said, the speed of a wave was determined by its medium, and the speed of a particle was unrestricted. Okay, but as we understood the real properties of light, the real nature of light, we realized that light is a mixture of all of these different combinations. It straddles the wall. It does not need a medium. It is quantized. It is localized. It does engage in diffraction and interference. It does follow the wave equation, and it's unique in nature in that its speed is always the same number at every place, at every time, and regardless of its source and regardless of who's observing it. That is the only entity in nature for which that's true. Okay, so let's look at some of these wave properties of light. The first is diffraction. So you can imagine, let's say you have ocean waves that are coming in from the left, and the white bars indicate the crests of each wave, and the black bars are the trough of each wave. The crest is where the wave is highest, the trough is where the wave is lowest. If these waves are incident on a barrier that has a hole in it, this yellow barrier, then some of the wave energy will get through the barrier, and it will create this very complex pattern that we see on the right. And in particular, please note that this central lobe is getting larger and larger, longer and longer in the vertical direction as it moves further and further to the right. So there's sort of this conical shape of the primary lobe increasing in size as it moves away from the barrier. And then there are these zones in which there is no wave energy, followed by a minor lobe, a secondary lobe, and another zone of no energy, and a third lobe, and another zone of low energy, and a fourth lobe. In fact, there are an infinite number of these side lobes on top and on the bottom. So this is a very complex pattern. And particles don't do anything like that at all. If a particle passes through a hole in the barrier, it just keeps moving along at a constant velocity as if nothing happened to it at all, because indeed nothing did happen to the particle. It either hit the barrier or it went through, hitting nothing at all. Waves also engage in a phenomenon called interference. which is critical to the mathematics of quantum mechanics. So if you have two waves of the same frequency, labeled A and B here, and on the left we see that the waves are cresting and troughing at the same time in unison. So mathematically we call that zero phase shift. And if those waves combine, then they add very simply, and you get a wave of twice the amplitude, twice the displacement vertically that you had in A and B. So twice the amplitude means 4 times the energy. Energy is proportional to the amplitude squared. And so in terms of energy, you have a situation in which 1 plus 1 equals 4. So on the left, we have what is called constructive interference, where the waves add because they have a zero phase shift, so they crest and trough at the same time. And on the right, we have a situation which is called destructive interference. And here you have the waves have a 180-degree phase shift, which means that when one is at its maximum, the other is at its minimum, and vice versa. So they are always opposite of one another, and when you sum the two of those, you get absolutely zero at all times. So this is a case in which, in terms of energy, 1 plus 1 equals 0. Over here, in terms of energy, you had 1 plus 1 equals 4, as energy is proportional to the square of the amplitude. So this is a very strange thing, much different than what we might expect, and certainly very different from anything that we would ever observe with a particle. If 2 pitchers threw baseballs across the plate, 2 baseballs would arrive. You'd never see 4 and you'd never see 0. So waves can do things that are uniquely different and quite distinct from the properties of particles. Okay, and if that hasn't convinced you that waves and particles have nothing to do with one another and are completely distinct, then all you need to do is look at these 2 equations for the motion of waves and particles in the absence of any force. So in the absence of a force, Newton's F equals ma tells us that the acceleration of the particle is 0. It just continues to move at its existing velocity indefinitely in the absence of a force. Whereas waves always move. They are motion. They can't, excuse me, we got someone else who had a problem. Waves are always in motion. They are motion. They don't exist if they don't move. And they obey this equation, the second equation here, which is clearly a lot more complicated than the equation that governs the behavior of particles. And embedded in this long equation is the velocity of the wave, the v here. And I know that a lot of people aren't that keen on math and are afraid of equations, but you should never be afraid of a long equation. Most of them are actually saying something quite simple, as is this one. This equation merely tells us that waves are smooth. They go up gradually and down gradually, and they continually repeat in exactly the same pattern. And they have no jumps, no places where the amplitude of the wave changes abruptly, and no kinks, no places where the slope of the wave changes abruptly. Every wave that satisfies the wave equation will be this smooth repeating pattern. Okay, so how does all of that describe, help us to understand light and describe quantum mechanics? Well, let's start with one of the most glaring failures of 19th century physics, of classical physics. This is related to the understanding of thermodynamics. And in that theory, the equations of thermodynamics classical thermodynamics said that any hot object would emit radiation, and it would emit the same amount of energy in each band of frequency. Since frequencies can run up to infinity, there are an infinite number of bands of frequencies, and if the same amount of frequency is emitted in each band, and that amount is greater than zero, then the total amount of energy emitted over all frequencies would be infinite. So if you were to strike a match, you would cremate the entire universe because the match would radiate an infinite amount of energy, destroying everything. Well, clearly that's ridiculous. So the question was, what was wrong with the theory of the classical theory of thermodynamics? Now, Max Planck said, he was one of the most famous theoretical physicists of the day. He said in the year 1900 that we could avoid this so-called ultraviolet catastrophe if we put a restriction on how atoms radiate energy. And that restriction was that they could only radiate energy in integer multiples of some constant h times their frequency f. The constant h is called Planck's constant. So the idea was that an atom could radiate an amount of energy that was equal to hf, or 2hf, or 17hf, but never 2.5 hf. The multiple of hf had to be an integer. This was what Max Planck proposed, without any explanation for why it had to be an integer. But if that restriction is imposed, it does solve the problem, which at that point was the only thing that mattered. So let me give you a sort of a numerical example here. This is just a made-up example. It's not realistic in terms of the values of things. We have frequency bands centered at 1 hertz, 10 hertz, 100 hertz, and 1,000 hertz. We're going to have the same amount of energy radiated in each band. So let's say that amount is 1,000 in some units. And let's say the value of h is 10, just for fun. So then we would, at this frequency band, hf would be 10. And to radiate 1,000 units, we would need to radiate 100 times hf, right? 100 times 10 times 1. Well, that's pretty simple math. If in the frequency band at 10 hertz, then 10 times 10 is 100, and so we have 10 units of hf being radiated. In the frequency band at 100 hertz, we have 1 unit being radiated, and at the frequency band of 1,000 hertz, we have 1/10 of a unit being radiated, and so on and so on. And integrating to infinity, we would have an infinite amount of energy being radiated, because in each band, we would have 1,000 units. The number of HFs would get smaller and smaller, but they would still have the same total energy radiated. So this was the picture in classical physics. Now, what Max Planck's solution did was to terminate this sum. So he said you can't have 1/10 of a HF being radiated and 100th and 1,000th and so on, ever decreasing fractions. You either have to have 1 or 2 or 0 or a bigger number. And so if you don't have enough energy to radiate 1, then you're stuck with no radiation at all. So there would be no energy radiated at 1,000 hertz in this case, and no energy radiated at any higher frequency. So that cut off the frequency at which energy could be radiated and left us with a sum which was finite. And that solved the problem. You light a match, you get a finite amount of radiation out. You explode a box of TNT, you get more radiation out, but you get still a finite number. Well, so mathematically, this was a solution, and Planck was happy with this mathematical trick, even though he had no physical explanation for why the the multiple of HF had to be an integer. He guessed that it was probably a property of matter, a property of the atoms, that they were unable to radiate at frequencies that weren't multiples of HF. So it was a solution without a solid explanation. Einstein believed that if this mathematical trick worked, there should be an underlying physical explanation for why these radiated energies had to be integer multiples of HF. And he ultimately figured out why. As we'll see, he discovered this by examining a mystery that had existed for most of a century called the photoelectric effect. There's a related mystery called the photovoltaic effect that had been around for more than a century also, and they both have the same solution. So let's talk about the photoelectric effect. The mystery was, if you shine light on a piece of metal, sometimes you will eject electrons. The mystery is the sometimes. It made sense that if you shine light, which delivers energy to the metal, you can kick electrons out of their atoms. The electrons are bound to their atoms with a certain binding energy. If you deliver more energy than that, then the electrons can be ejected from their atoms. They can be torn away from their atoms and leave the metal. So it made sense that light could do this. What the mystery was that yellow light would be able to eject electrons. Even if there was very little yellow light, you would still eject some. But if you used red light, you would never eject any electrons. Even if you made an extremely intense beam of red light, you would get no electrons ejected at all. And that didn't make sense in terms of classical physics, because both yellow and red light carry energy. Just go out in the sun without sunscreen and you'll realize that quite quickly. And so what was wrong with red? What was wrong with the energy delivered by the red light compared to the energy delivered by the yellow light? And Einstein's solution to this mystery was that actually light is both a particle and a wave. Two things that everyone else in the world believed were completely incompatible. So this proclamation of Einstein's was nothing short of heresy. He said that the yellow photons have a higher frequency and therefore they have a higher energy. All photons, he said, have an energy equal to h times their frequency. The red photons have a lower frequency and a lower energy. And at the atomic level, what is happening when you shine light on the metal is that there are a stream of individual particles of light that come in, and some of them will hit an atom in the metal. And at the fundamental level, what is happening is only one photon can hit one atom at a given time. There simply aren't enough photons in any normal beam of light for two of them to hit at the same time. So if that one photon has enough energy to overcome the binding energy of the electron in the atom, then this electron can be ejected. If the one photon that hits does not have enough energy, then the electron cannot be ejected at all. And it doesn't matter how many friends the red photons have that are hitting atoms in different places at different times. There's no double teaming here. And so none of the red photons will have enough energy to eject an electron, but each of the yellow photons will, because their frequency is higher. So, and this is a direct consequence of the fact that Einstein said that light has a particle property in addition to having a wave property. So by declaring that that light was composed of individual particles, which we call photons, we now understand why the photoelectric effect makes a distinction between different frequencies. And we also understand why the energy emitted has to be, by an atom, has to be an integer number of HF, because the atom has to emit an integer number of photons. Photons are particles. They're quantized. They come in integer numbers. So an atom might emit 1 photon or 2 photons or 17, but it can't emit 0.1 photons. So that explains why Planck's solution to the ultraviolet catastrophe actually worked. Interestingly, even though Einstein had reinforced Max Planck's suggestion by providing a physical rationale, Max Planck never accepted the fact that this notion of photons was really true. He went to his grave believing that photons were classical waves, that they were not quantized in particles, and he just couldn't accept the fact that, that the universe could be anything different from that. And it's remarkable sometimes how these brilliant people can understand an incredible amount in one direction and nothing to the side. I guess it's a phenomenon of the human mind. Okay, well, following Einstein's heretical suggestion that light was both a particle and a wave, Louis de Broglie extended Einstein's idea, which led to the fundamental principle of quantum mechanics, which is called particle-wave duality. And that fundamental principle tells us that everything in nature is really both a particle and a wave. Everything in nature has both particle properties and wave properties simultaneously. And that is an enormous departure from classical physics and is the fundamental principle of quantum mechanics. From that fundamental principle, all the consequences of quantum mechanics can be derived. Now, in particular, this particle-wave duality tells us that waves are quantized in units. Light is quantized in terms of photons. Sound waves are quantized in terms of something we call phonons. And all waves, we believe, are quantized in some fundamental units, depending on the nature of the wave. It also tells us that particles have wave properties. In particular, they have wavelengths. This wavelength that we symbolize with the Greek letter lambda will always be this Planck's constant divided by the momentum, according to Louis de Broglie. And that also has enormous consequences in the theory of quantum mechanics and in understanding nature at a more fundamental level. So in particular, it helps us understand atoms. And since everything that we see in the universe is made of atoms, we can't make much progress in understanding those things if we don't understand the true nature of atoms. Now, if we look around us at the macro world, it seems that everything we see is a uniquely different entity. Every galaxy seems to have a different number of stars, a different shape in detail, a different mass. Every tree is different from every other tree. Every leaf is a little different from every other leaf. All people are different from one another. Even identical twins are typically not indistinguishable. And in fact, even every humble snowflake is uniquely different in some minor way than every other snowflake in existence. So there are literally trillions upon trillions of uniquely different things that we observe in the universe. And if that was the end of the story, then there would be no science and there would be no engineering. There's no way that the human mind could wrap its head around trillions and trillions of uniquely different things. We just simply don't have enough neurons to cope with that level of complexity. we could never build bridges, or because we wouldn't know if this piece of steel was how it related to other pieces of steel. How strong would it be? But the story doesn't end there, fortunately, because if we take apart all of these diverse things that we see in the macro world, we discover that they're all composed of compounds and molecules. And there are only millions of different types of molecules. Millions of millions is certainly a lot, but it's much less than trillions of trillions. And indeed, there are only about 10,000 molecules that occur naturally, and the millions of molecules are those that are created by life. So I'm told that the human body produces about 1 million different types of proteins. Other species produce other proteins, and if you look at all of the different species, you get the millions and millions of molecules that these species are producing. But inanimate life, abiotic life, only is capable of producing about 10,000 different types of molecules. So in any case, going from the macro world to the level of molecules, as we descend to that smaller scale, we have greatly reduced the diversity of nature. There are only millions and millions instead of billions of trillions of trillions. And if we take apart the molecules, we discover that they're all made of atoms. And even if you count all the isotopes of all the different elements, there are only several hundred of different types of atoms that exist in the universe, that could exist in the universe, indeed. So we've gone from trillions of trillions to millions of millions to hundreds. And now we're making great progress in simplifying things. And finally, if you take the last step, we currently believe this is the last step. We've said that before and been wrong, but now we think we're right. If you take the last step, you get to the level of individual particles of nature. And for our purposes today, we're going to talk about 4 of these particles. There are some more that we'll talk about later, but for today, we'll talk about just 4. The photon is the particle of light. We've talked about that. And the 3 other particles listed here, the electron, the proton, and the neutron, are the particles that make up all the atoms that exist in the universe. And the exciting thing about these particles is that every single electron in the entire universe is exactly identical to every other one. There is absolutely no distinction, no measurable difference between 2 electrons anywhere in the universe. And what I'm saying is not that humans aren't able to find a difference. It's much more than that. Excuse me. It's much more profound than that. Nature itself, there is no phenomenon of nature in which 2 electrons are distinguishable in any way whatsoever. And we know that's true because if it weren't true, atoms would immediately collapse. And they don't. So the quantum theory tells us that the reason they don't collapse is that the electrons are all identical particles. And the protons are all identical particles to one another. The neutrons are all identical to one another. The photons are all identical to one another. This is in terms of all of their intrinsic properties. They may have different energies, they may be in different positions, they may have different external properties, but their internal properties are exactly identical. There is, at this level of nature, virtually no diversity whatsoever. We're talking about 4 particles. In classical physics, we were talking about 2 forces, and both of those are numbers that are small enough for the human brain to comprehend. So it's this decreasing diversity of nature at the micro world that makes science possible and engineering. Okay, so let's talk a little bit about these 4 particles. We talked about the photons before. The first discovery that electrons existed was by J.J. Thomson in 1897. And he used a device that's somewhat similar to what I've drawn here. What I've drawn here is a classical vacuum tube television, which probably still exists somewhere, but I don't know where. Nowadays, most of these things are solid state devices. Anyway, in a classical television, you have a so-called cathode, which has a negative voltage.
Professor, I have one of those televisions in my home.
Oh, good. So if everyone else has a solid state television and you want to see what a vacuum tube television looks like, you can go visit Shabam's home. I'm sure he would be gracious to welcome you in his house.
Yes.
It's unfortunately quite a long trip. Okay, in any case, so you have a cathode which you apply a negative voltage to, an anode that you apply a positive voltage to. The electrons are negative, so the electric force pulls electrons out of the cathode. This anode is more like a screen door than a solid piece of metal, and so many of the electrons pass through, and then you have either magnetic or electric devices here that cause the beam to deflect in a controlled manner, and you can scan this electron beam across the two-dimensional surface of the TV. And so that's the fundamental way in which televisions work. They didn't have TV in 1897, but J.J. Thomson used a device that's relatively similar to this to discover that these beams of energy that were hitting the screen were actually made of individual negatively charged particles, which we call electrons. The next major advance in the discovery of these particles was made by Ernst Rutherford, the New Zealander who moved to do his physics in England. And in 1909, he made a discovery that atoms have a nucleus, as we call it now, which is a very small, which occupies a very small volume compared to the volume of the atom, and in which almost all of the mass of the atom is concentrated. So there is this very low mass external structure, which we now know is occupied by electrons in orbit around the nucleus, and a very small structure with extremely high density at the very center that contains all of the positive charge that attracts the negatively charged electrons. And he discovered that this was a very small, high-density object by exposing these atoms to beams of alpha particles. An alpha particle is the nucleus of a helium atom. And some of these alpha particles were very surprisingly discovered to be reflected at extremely high angles. So what was expected was more like this fourth from the top arrow, which has a slight deflection, and that's what you would get if there was a distributed charge over a larger area. In order to get a very high angle reflection, you need to have a small object with a very high mass, so that the alpha particle is bounced off. The alpha particle itself has a substantial mass, and so this object has to have a lot more mass than that. In fact, he used these atoms that he was exposing were gold, so they have a very high mass indeed. And Rutherford is said in announcing the discovery that it was the greatest surprise of his life that these alpha particles bounced almost directly back in some cases. And he said it was like firing a cannon at a tissue paper and having the shell come back in your face. And that's only explainable if the tissue paper contains these small objects of extremely high density. Okay, so with those discoveries and with quantum mechanics, we now understand the structure of atoms. At first blush, they have just two parts. They have a cloud of electrons, which is in orbit around a nucleus. The electrons each have a negative charge. The nucleus has a positive electric charge. Opposite charges attract each other with the electric force, and that's what keeps the atom together. So atoms are very small, much too small for us to perceive with our normal senses. If you were to line up 1 billion carbon atoms in a row, they would be about a foot long, 30 centimeters if you prefer. The electron cloud, that's the size of the electron cloud, about 1 billionth of a foot. And the electron cloud is actually 100,000 times larger than the nucleus in typical atoms. So as small as an atom is, the nucleus is vastly smaller than that. If you were to make the analogy that you enlarged an atom until it filled a major sports stadium, like a football stadium or a soccer stadium, then the atom would still be about the size of a head of a pin, sticking out in the middle of the field. But as small as that nucleus is, it typically contains as much as 99.97% of all the mass that the atom has. So the electrons are very low mass compared to the particles that make up the nucleus. And the amount of energy that's in the nucleus is millions of times more than the amount of energy that's in the electron's cloud. The nucleus is composed of individual particles. These of two types. They can be protons and neutrons. The protons are the particles that have the positive charge that gives the nucleus the charge necessary to attract its electrons. And the neutrons have zero electric charge. Every atom has at least one proton in its nucleus, and the atoms in their nucleus will have either 0 or 1 or 2 or more neutrons. So the simplest atom is hydrogen, 1 proton and no neutrons, and the atom depicted here is helium, 2 protons and 2 neutrons in the nucleus. The number of protons and the number of electrons in a neutrally charged atom are equal, this being -1 each, and the protons are +1 each. Okay, so before quantum mechanics, this notion that electrons circulated around nuclei in a similar sort of way that planets circle the sun, that didn't hold water in classical physics, because any charged object which is accelerated, according to classical physics, has to emit radiation, has to emit what we now know is photons of light. So in order for an object to go round and round, it needs to accelerate. It can have a constant speed, but its direction of motion, the direction of its velocity vector is continually changing as it goes around. And that can only happen if the particle is being continually accelerated. The acceleration is provided by the force of electricity between a positive and a negative charge. The Earth is also being continually accelerated as it goes in orbit around the sun, and in that case, the force is obviously the force of gravity. So any object that's in motion around something else must be continually accelerated to maintain that orbit. And if the electron was accelerated, and if it did emit radiation as a result of that, as classical physics mandates, then it would lose energy. The photon would carry away some of its energy, and the electron would spiral closer and closer to the nucleus. It would keep emitting electrons until finally it fell into the nucleus. And this would be a very bad thing, because that would make the atom about 100,000 times smaller. The electron would be absorbed into the nucleus and unite with the protons perhaps and form neutrons, and you would have no atoms at all. So the Earth would collapse to something only that would be 100,000 times smaller than it is. The sun would, well, this does not apply to the sun because the sun is not made of neutral atoms, but it would apply to all the planets. And in this case, clearly there would be no opportunity for life. So the dilemma that was facing classical physics is, why don't atoms collapse? Why don't these electrons orbiting in the atoms continually radiate energy and cause the atoms to collapse? Okay, so quantum mechanics provides an answer to that question and tells us why atoms are stable. If you think of this diagram on the left, there is the nucleus, the yellow dot at the center. We will imagine that the electron is orbiting within this green band, and we'll cut the green band at the top at the place labeled A, and we'll stretch the green band out horizontally just for illustrative purposes. As the electron goes around and around, we know that the electron has a wavelength, according to de Broglie. And if we start at this position, let's say over here, with the wave at the minimum, as we go round and round clockwise and get back to A, the wave of the electron will be going up and down, up and down, up and down. Remember, it's a wave, so it has to be smooth, and it ends up at some value at A. Well, A on the left is the same as A on the right. This is as if we had taken a map of the Earth and cut it at the international date line. If there is an island on the international date line on the left, there has to be the same island on the international date line on the right, because these are the same places on the surface of the Earth. And A in this case, are the same places in the atom. So it's not possible for this wave to exist, because here it's a minimum and here it's a maximum. So it would have to abruptly change from minimum to maximum, and that can't happen to an object that obeys the wave equation. That's an abrupt jump, and there are no jumps in the wave equation. So this is not a valid orbit of the electron, quantum mechanics tells us. This is the orbit of the electron must oscillate up and down an exact integer number of times so that it has the same value and the same slope at the beginning of its orbit and at the end of its orbit, which are the same place in space. So the circumference of an electron's orbit, 2 pi times its radius, must be some integer times the wavelength. There has to be an integer number of these oscillations all the way around the orbit. And that's the condition of an allowed orbit. Anything that doesn't have an integer number of waves is not an allowed orbit, because it doesn't satisfy the wave equation. So an electron cannot orbit a nucleus at any radius whatsoever, as planets can orbit stars at any radius. But in the case of atoms, electrons can only orbit the nuclei at specific radii, at radii for which the number of oscillations of the wave function, the number of wavelengths, is equal to an integer. So there will be one orbit close to the nucleus in which there is one wavelength of the electron all the way around. Further out, there's one in which there are two oscillations of the two wavelengths all the way around, another with three, and so on. In all the atoms on the periodic table, the furthest out this goes is about 7. is 7, not about 7. It's exactly 7. Okay. So an electron in the first orbit is close to the nucleus, so its binding energy is the strongest. So that means binding energy is negative, so it's the lowest energy, the ground state it's called. The electrons in the second orbit have a higher energy. Electrons in the third orbit have an even higher energy, and so on. So because there are only a specific discrete number of these orbits, there are only a specific discrete number of energy levels in an atom that an electron can have. There cannot ever be an electron with an energy that's in this range, because that electron would have a non-integer number of wavelengths in its orbit, and that's simply not permitted. Okay, well, if you have this small discrete set of energies and an electron moves from one to the other, let's say an electron started off in the energy level 2, and as everything in nature, things seek the lowest possible energy, so it would like to descend to the lower energy, being closer to the nucleus, being more tightly bound. And so its energy would change from what we call E2 to what we call here E1. And to conserve total energy in the universe, that difference in energy, E2 minus E1, has to be carried off by a photon. This particle of light will have an energy, which is Planck's constant times its frequency, that has to be this quantity here. It can't be, it can be E3 minus E1, it can be E3 minus E2, various combinations are possible, but there are only a small integer number of such combinations, and you cannot have any combination that corresponds to energy levels that are in between, because none of those are permitted. So for each type of atom, for each nucleus that has a certain positive electric charge, each element on the periodic table that is, there are a discrete set of energy levels that the atom can emit radiation at. And here are 3 examples. So hydrogen is the simplest, 1 proton, 1 electron, and these bars represent the frequencies of light that hydrogen atoms can emit or absorb. Helium has 2 electrons and 2 protons. It's a more complex atom, and it has quite a few energy levels. And carbon has 6 and 6, and so it has even more energy levels. And every element on the periodic table will have a set of frequencies like this that its atoms can emit and absorb. These are called spectra, the spectrum of frequencies that its atoms can absorb and emit. And they're all unique. They're all different. They're different because the total positive charge in the nucleus is different for each element on the periodic table. So we can measure the position of these frequencies with extreme precision to as many as 15 decimal digits, and we can tell you whether light is emitted by carbon atoms or helium atoms. And we can tell you that no matter how far away the source of light is, because the frequencies will simply be different. This is a unique fingerprint of carbon. This is a different and unique fingerprint of helium. And every element on the periodic table has this unique fingerprint that exists in the light it emits or absorbs. So in 1842, the French philosopher Auguste Comte said there were things mankind will never know. And that's probably true, but the specific example he gave was the chemical composition of the stars, which seemed like a good bet at the time. After all, how would we get to a star? How would we scoop up a bit of star? How would we take it back to our labs and analyze it in our chemistry labs and find out what its the abundance of all the different elements was? It seemed to be a completely ridiculous prospect. However, within just a couple decades, the science of spectroscopy evolved, and now we can precisely determine, excuse me, we can precisely determine the composition of every source of light in the universe. So we can measure the composition of every star that we can see. We can measure the composition of galaxies. We can measure the composition of the dust clouds that surround them because they absorb some of that light. And we can precisely know how much hydrogen there is, how much oxygen there is, how much carbon there is, how much helium in everything that exists in the universe. And we don't have to leave the Earth to do that. We just look at the light that either is absorbed or emitted by all of the objects in the universe. So Auguste Comte may be right about something, but he was certainly wrong about the chemical composition of the stars. Okay, that's the end of what I wanted to present today, a brief introduction to quantum mechanics. And the most important parts were to understand the structure of atoms and also to understand the unique fingerprints of light that those atomic structures result in. So the rest of the time is open for questions.
Robert, I had a question.
Gil.
And maybe in one of your subsequent series, you're going to discuss this in more detail. But I have a difficult time in talking about the structure of an atom in relationship to the fundamental particles. Do we have any idea what fundamental particles look like in terms of a diagram? Is there a picture that you can present of quarks or leptons? And I thought an electron is a lepton. Do we have a picture of those kinds of things that is talked about or reviewed of subatomic particles?
Yes, okay. So we're going to talk about particles in a subsequent series, subsequent seminar. But particles aren't like going to Africa and looking at all the different animals and taking photographs of zebras and giraffes and elephants and lions and tigers and bears. We can't see particles. We can detect things they do. We believe that the fundamental particles have zero size. We know that if they didn't have zero size, we know that the size has to be extremely small. It has to be maybe 1 million times smaller than a nucleus. Quantum mechanics says they have zero size. They don't have color. They don't have shape. They are just numbers. Our description of these particles is simply a set of numbers. We don't draw a picture of an electron. We think it's just a point in space. It's a point in space that has an electric charge. It has some amount of angular momentum. It has the property of being a lepton. And it can have external properties like an energy and a velocity and a position and so forth, but it's just a set of numbers. And we have no knowledge of anything else. And we never will. We have to make instruments out of atoms. That's the only thing we have to build with. And those atoms are enormous collections of these particles. And so we're not delicate enough to explore the inside of an atom in any meaningful way, except we smash them together and we looked at, you know, the tracks they leave and so on, but it's not a direct experience. I guess long ago I gave up on that notion and it doesn't bother me anymore, but since you bring it up, maybe I should be bothered by it because it makes particle physics in a sense less fun than looking at giraffes, right?
Right. I'm still bothered by it. And particularly when you say that a proton is made up of quarks, two up and one down, and a neutron is made up of two top and, I guess, one top and two bottoms. If we can't picture that, we're just picturing numbers.
Yeah, well, the quarks, you could imagine three little balls going around in orbit around one another, and the three little balls all have zero size. They're the fundamental particles, the quarks. But that doesn't help much, does it?
That's why I wonder how we know that there's 17 and not, 170.
Ah, yes. Well, that's a little bit more complicated question. So I will put that off to a later seminar. There are 17 of these particles that we believe are indivisible. They have no internal parts. In fact, we believe they have zero size, despite having electric charge and so forth, and angular momentum. And there are hundreds of particles that are composites, like the proton and the neutron. There are hundreds of these things, most of which are very uninteresting because they live no longer than a trillionth of a second. But I mean, particle physicists get excited about discovering the 375th, but no one else should get excited about it. We know that there are not more than, the Higgs boson is the 17th, and there are theories that propose that the Higgs has some cousins that we haven't seen yet. But if you ignore the Higgs particles for a while, the rest of the 16 particles, we have good reason to believe, and we can talk about why in a subsequent seminar, but we have good reason to believe that there aren't any more than that. And for 12 of those 16, there are antiparticles. For the other 4, they are their own antiparticles. So it's the 16 particles of 12 particles of matter, 12 particles of antimatter, and 4 particles of forces. And we're going to talk about, it's hard to wrap your head around what I just said if you've never heard about this before. And we're going to have 3 sessions on particles and what's the story with these particles, what groups of particles there are, what characteristics the particles have, and how we have discovered them. So there are going to be 3 seminars on that as part of our category on particle physics.
Well, Professor,
Yes, sir.
I do not have a question, but I wanted to say one thing.
Yes.
That in the very beginning of this year, I have done that experiment we just talked about, that J.J. Thomson's cathode ray tube experiment.
Oh, you did? Did you find nuclei? Maybe not. Okay, Michael Beeson?
Robert, you said that Planck never believed photons were more than a mathematical fiction.
Yes.
And when you and I were at Caltech, Marie Gelman was just working on quarks, and the general belief on campus was that quarks were merely a mathematical fiction and were not, quote, real. And yet
Yes.
now, in the intervening half century, quarks have become real. So please comment on particles and reality.
Well, from a, I guess from a, as a physicist, I would say that our definition of what we consider to be real is when we have a description that explains the observations that are made. And that is not real with a capital R. We know many things about electric charges. We know how electric charges exert forces on one another. We know the electric charge of all the particles. We've measured the electric charge of the electron to, I don't know, 12 decimal digits, but we have no idea what electric charge is. Fundamentally, we have no understanding of what electric charge is. We have no understanding of what mass is. We have no understanding of what energy is or anything else. If you keep asking what, you get to a point when we can't answer the questions. So physics is not about describing what is real in a sense. Physics is about describing how the things we observe interact with one another. And quarks are real in the sense that they help us make a better description of how particles interact. There is a physicist who I greatly admire, Carlo Rovelli, who happens to be Italian, by the way, that helps. Anyway, he says that the only reality in the universe is relationships. That a thing that has no relationship to anything else has no basis for being called real. And an electron is how it relates to the other particles. And in and of itself, it isn't anything. Now, I don't know if I buy 100% of that, and I don't know if that's how many physicists would buy 100% of that, but there's a lot of truth in that. We describe relationships in physics. We don't describe reality.
Robert,
Yeah.
could you explain how the Higgs boson changed everything when it became evident what its characteristics were?
Well, the Higgs boson was proposed, I think, in 1972. And it was proposed as an explanation, quote unquote, for why the fundamental particles of nature have masses. I'm not a super fan of the Higgs boson, but that puts me in a distinct minority because we, as a community of physicists, have probably spent $20 billion to find the Higgs boson.
Wow.
So it's incumbent on physicists to say that was a great accomplishment. Otherwise, we won't get more money. But since I'm not in the mode of having to raise money for my research, I can tell you what I really believe, not what I have to say to get money. Okay, so before the Higgs boson, there were 16 known elementary particles. Each of them has some associated mass. The photon has 0 mass, but still that's mass equals 0. That's a number. There were 16 numbers, which were the masses of the 16 particles. And science had no explanation for why the particles had those numbers. Why is the electron lighter than the proton? Why is the proton mass 938 point blah, and so forth. So we had this gap in our knowledge. We couldn't explain the 16 masses. So Peter Higgs and about 6 other theoretical physicists got together and they proposed this notion that there would be a new particle, which got named the Higgs boson, which would interact with the existing 16 particles in a way in which the Higgs boson provided each of those particles with a certain amount of inertia, which is mass. So the Higgs boson was intended to explain the 16 values of mass. Well, the explanation is the heavy particles interact more with the Higgs boson than the light particles do. So instead of having 16 masses, now we have 16 coupling constants, for which none of them are explained. Right? So we traded 16 unknown masses for 16 inexplicable masses. They were well known, but inexplicable, for 16 inexplicable coupling constants. So I don't know if that's worth $20 billion.
Wow.
I mean, it's your money, not mine. You tell me if it's worth $20 billion.
Well, why is it called the God particle?
Because that's publicity.
Oh.
That was marketing PR. Now, you don't get $20 billion just for being handsome, you know, or you got to talk a lot to convince governments all around the world to fork out $20 billion. The Higgs boson is no more divine and no less divine than any of the other particles. And it accounts for about 1% of the total mass of all normal matter. Not 100%, 1%.
Professor,
Yes.
I have 2 thoughts. My experience suggests the energy levels are equivalent to valence levels. And number 2, the relationship between electrons and proton is about 1800. I can't remember exactly the number, but that's what my background suggests. How close am I?
You're absolutely correct in both cases.
Okay, thank you much.
So the energy levels, chemists would, as a physicist, I would describe those as energy levels of the electron, and chemists were more likely to describe it as the valence levels.
Okay,
particularly the outermost levels, the highest energy levels of the electrons are where all the chemistry happens. And that's the focus, obviously, of the chemists, and they call that the valence states. And the ratio between the proton and the electron in terms of mass is 1,800 and something. So you're right on both cases.
thank you.
Robert, may I ask one more question?
Sure.
You had a graph showing the de Broglie's matter waves, and you didn't label the y-axis, and I do not know what the units on the y-axis are.
Okay, I'm not sure which graph you're talking about, Mike.
The one where you had the graph going from A to B to A again after.
Oh, yeah.
What's the
Okay.
unit on the y-axis?
Maybe I can get that back. That's it? Mike, is that it? Well, I think it's it. So I guess you turned your microphone off.
I don't know what the units on the y-axis are there.
Well, yes. This is illustrative. It's not meant to be a precision diagram. Anyway,
Well, what's vibrating?
this is the amplitude of the electron wave going up and down. The electron has wave properties, and so it has a wavelength, and this is the electron's wave. So the wave property of the electron is its quantum mechanical wave function.
So we're looking at the probability of it being found at a given point on its, quote, orbit.
Right, the probability amplitude. And this is the real part of a complex function.
But I observed you've drawn that like a strip of paper.
Yeah.
If you were to give it a half twist, then you could make that forbidden wave match up, like a Mobius band.
Yes, but
then
you know,
can't.
the strip of paper is the strip of paper doesn't have a physical reality to it.
And you can't do that because the amplitude is actually a complex number and not a real number.
Right. Right.
Got it. All right, thanks.
So for those of you that didn't find that amusing, I'm sorry, but that's you know, that's the kind of thing techers talk about, right? Other questions?
Robert?
Yes, Jill.
Robert, can an electron go to a higher level orbit ever? I know you say it goes from a higher level to lower and emits a photon, but can it ever go the other way?
Yes, I should have made that clear. Yeah, that's a good point. So if you shine light on an atom and the light has exactly the right frequency, the one electron could absorb one photon of that light, and it would rise to a higher energy level.
So what happens when it absorbs the photon?
So it would rise to a higher energy level, which would be an orbit that's further away from the nucleus. If the energy of the light was sufficiently high, the electron would be separated from the atom completely.
Oh, okay. Thank you.
But yeah, sure, which is what you see in the photoelectric effect. So for example, if you have a break, let's say you're talking about cosmology, you have a very bright source of light that's extremely far away, and the light is coming toward the Earth. So imagine now that you have a cloud of dust that's in the way, and that dust absorbs some of the light. So we would see that the light that's reaching Earth is missing some frequencies.
Oh.
And the frequencies it's missing are the ones that got absorbed by the dust.
Interesting.
And the dust is only going to absorb light at the frequencies at which its atoms have the right spectra. So we can tell you how much carbon is in a dust cloud.
Fascinating.
I mean, it's amazing how powerful all of this stuff is.
Really?
And if these spectra didn't exist, we wouldn't know the universe was expanding.
Wow.
But that's a topic for a different seminar.
Great topic.
Robert, can I ask you to carry that a little further, and maybe you don't want to do it now? When we talk about the spectrum of light and starting from gamma rays to radio waves,
Yes.
is it possible that there are other light waves that we have not discovered in between or even outside gamma rays and radio waves?
Well, that plot is the horizontal direction across the plot you're talking about, which I haven't shown today. So for those of you that don't know what we're talking about, that's why you don't know it. I'm sorry. I didn't show that plot. But if you make a graph along a line, so it's not really a graph, but you're going across a horizontal line, And that horizontal line is energy. Or equivalently, you could say it's the frequency of the light. So the frequency goes from 0 to infinity. So this is an infinitely long line. And at different places along the line, human beings have assigned names to the photons that have that energy. So this is a anthropomorphic thing, right? I mean, nature doesn't care about what names we give things, but we give them names so it's easier for us to have conversations with other people. So the lowest energy light is microwaves, and then there's a band of within at a higher energy that's radio waves, and the next up band would be infrared. Then you get the visible spectrums: red, green, yellow, blue, violet, and above that is ultraviolet, and above that is X-rays, and above that is gamma rays, and that this line goes to infinity, and we have labeled it sort of arbitrarily, you know, different pieces of the line, but that's just how we use it, how we describe it. There's whatever energy the photon, any given photon has, it's somewhere along that line. Energy is a single quantity, so it's a one-dimensional line. There is nothing that could be outside that line, right? Every energy would be at some point along this infinitely long line.
Where does laser fit in there, the light amplification in that spectrum?
Well, typically lasers are visible light. They don't have to be visible light, but most of the ones that are useful are visible or slightly infrared. The first discovery of that phenomenon, a maser stands for microwave. This is the same physical phenomenon, but at a microwave energy. Laser is that phenomenon at a visible light energy. But you could make, you could use the same physical phenomenon and make a device at any energy in principle. It's an engineering issue as to whether or not you can find the right materials, but you know, from a fundamental physics point of view, it would be the same phenomenon.
I have a question.
Yeah, Mike. The other Mike.
When you talk about electron orbits, you didn't mention the Pauli exclusion principle that,
Yes.
that prevents leptons from being in the same state. And I don't recall if this was a consequence of something that comes out of quantum mechanics, or if that's just a separate concept.
Yeah, Mike. So, yeah, we didn't discuss everything about atoms today. Just sort of a beginning. And we didn't discuss everything about particles. But the Pauli exclusion principle is a principle of quantum mechanics. And you can actually prove it mathematically that it's a consequence of the other aspects of quantum mechanics, particularly the fermions, the particles of matter, have spin 1/2, and so that makes it the fact that it's spin 1/2 results in the Pauli exclusion principle. The bosons, the particles of forces, have spin either 1 or 0 or 2. And so there is no exclusion principle for them. And in fact, the corresponding principle for bosons is that they are highly gregarious. The more of them that are in one state, the more likely it is that an additional particle will join the same state, which is what makes a laser work. But so so the distinction is directly related to the spin of the particle.
Okay.
And the consequence of the Pauli exclusion principle is you can't have any two identical particles of matter that exist in exactly the same quantum state. But we will talk about that when we talk about particles. So for those of you for whom none of that made any sense, don't worry about it. We will make it make sense later. Okay, any last questions? Okay, I want to say a few words about the topics that all of you voted on. And so I tallied them up, and we have about 26 topics on the list. So we've got a year's worth of stuff. The fact that we don't do something right up front doesn't mean we won't get to it later. And I guess, as I described in my email today, I propose that we do the following. We take the most popular topic in each of the 4 categories, and we use those 4 topics to complete our seminar series. So we have 4 remaining seminars in this portion, in this first session. It was a 3-month-long session. This is the second, and we got 4 more to go. And so I want to talk next time about astrophysics, which is all about stars, how stars are born, how they live, and what keeps them going, and then how they die, and the remnants that they leave behind when they do die. So that was the most popular topic in the category of cosmology. In space exploration, the most popular topic was what telescopes will come after the Hubble. So I want to talk about, there are a lot of telescopes that are being built, some of them on the ground and some of them intended to be launched in space. And so I'll talk about either 1 or 2 of the upcoming space telescopes in a seminar to be in the future. In the next 4, we're going to talk about in the category other, the one that got the 2 topics got 3 votes each, which was the largest number of votes. And the topic that I think we should talk about first is the special properties of Earth and the universe, and whether, some people say that these special properties indicate that the entire universe, for example, was finely tuned to enable the existence of life. And you may agree with that or not, but why don't you listen to how special it is before you make a decision. And then the last one is in the category of particle physics. So I'm picking one from each of the 4 categories. The leading vote getter was the 1970 accelerator experiment, but that's part 2 of a 3-part series. So, which is all about particles, that's the series. So we will get to that, but not immediately. We have to first discuss the first experiment, the first particle physics experiment in history, and that discussion will also include a discussion of the more stuff about the particles. We'll talk about the 16 particles and their basic characteristics. So that's my plan, and we'll see you all next week. In 2 weeks, and we'll talk about stars. So thank all of you very much. If you have questions that didn't get answered about today's seminar, you can address them to my website, which is given, the address is down here, or all of you have my direct email address, you can use that too. And if you're looking for reading material, then these books I think, are a bargain at the price, and they will tell you as much or maybe even more than you ever wanted to know about any of these subjects. So thank all of you, and we'll see you all in 2 weeks.
Please thank Joan for everything she's done to make this so smooth.
Hey, Jill,
Yes.
there's a guy here who introduced me to Joan and on a blind date over
What?
55 years ago.
Well, what a smart guy.
Yeah,
5 years.
Who is that?
yeah. Well,
He
that,
That
that
would
remain a secret for now.
no, I don't mind. That's me,
Oh, it is? Michael?
Michael.
Whoa. Oh, you were at Caltech then. Wow. Good job, Michael.
Okay,
That's
thank you
wonderful.
all. Bye-bye.